SVM is a supervised machine learning algorithm which can be used for classification or regression problems. SVMs are very good when we have no idea about the data. They work well even with unstructured and semi-structured data like text, images, and trees. Understanding this, we have come up with this tutorial on support vector machines. Now, before we go ahead with the session, I'd like to inform that we have launched a completely free platform called as Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. You can check out the details in the description below. Let's have a quick glance at the agenda. So we will start off with an introduction to support vector machines. Then we will learn about kernels in SVM, following which we will look at the properties of SVM. Finally, we will go through a case study.
SVM is what we call as a support vector machine. As I said, this was designed in the year 1971. Now, one of the core advantages of SVM is non-linear data, right? Especially data that have no separable or no linear boundaries I can draw. So logistic regression will start failing there. Linear regression might never do anything there about it, right? Or any other classifier, naive, Bayes, KNN. So these guys start failing when there is a non-linear separation or there is no overlap or there's not a distinction capability. Now SVM brings in a brilliant complexity or brilliant feature to the model where it is able to understand the data in its entire sense of complexities, all the associated complexities. So it's not worried about multilinearity, it's not worried about autocorrelation, but it's more fail safe and tolerant towards those attributes. Right? So that's the key core advantage of support vector machine. The key objective: draw a hyperplane and use this hyperplane to separate two classes. And this hyperplane is drawn by what we call as supporting vectors on each side of the class. And what we call the technique or the approach is what we call as the widest margin road approach, right? So this is the widest margin road approach. So if we want to look at it, right, it's a pretty simple thing. I have my data here, and I have two classes. This is my positive class, and this happens to be my negative class. Now, the concept of SVM is to draw this particular hyperplane that will separate out these two classes with the most possible and widest margin possible by taking into account these objectives. So this is called as the hyperplane, and this is called as the gutter or margin roads. This approach is called as the widest margin road approach. So basic idea: have a separation hyperplane W that is having the maximum possible distance D, right? So this is a distance D. So this is to ensure that the model is robust, it is fail-safe, it does not have a misclassification in any sense and factor, right? That's the reason we call this as the widest margin road approach. So the key objective: keep the distance between these two classes as wide as possible in order to ensure that the separation is always high, right?
Shyam, one doubt I had was when I was looking through the videos was we can draw a line like this with margins, right?
Right.
In certain cases, and that was evident from the example in the video, because if you had removed one point from that that data set, then there would be another line that would also fit properly, separating out the values. Now, how do we decide which is best?
No, see, okay, so if I want to answer your question, your objective is if I remove this point, right? Let's say I'm removing this.
And also some from that minus as well.
Right. So I'm removing a few points from here.
Correct.
Correct?
Yeah.
Now, what happens is if I remove them is, remember my objective. So the reason I'm not spelling out math, but I'm probably allowed a light bit of math here. So the core objective of support vector machine is to maximize the distance between the data points or having a maximized distance between the two clusters, right? So this part is clear in terms of understanding, correct?
Yes. Yeah.
Now, the maximized can only be possibly one value. A maximum or the highest can only be one value, correct? You agree with me? So the highest distance, or if I want to separate two classes, the highest distance I can achieve is only one value, correct?
No, that depends on how the values are distributed, right?
Correct. So let's look at it, right? Either way. So if I probably look at this, if I look at only these set of data points here, I can only have one possible distance that is the most optimal way of looking at it. Or if I take a max from any data set, it can only be one value. I can have multiple maximum values, but the highest can only be one, correct? So the highest value in a data set can only be one. Let's say 1, 5, 7, 2, 11, 13.
Okay.
Now if I call from max in this, it can only be one value.
True. Yes.
Agreed, there are more than one occurrence of the max, but generally if I compute it, I can only find only one max value.
Right.
Right. So in similar case, but the core objective of support vector machine is to maximize the distance between the two planes and find the midpoint and use that as a hyperplane. Correct?
Okay.
You agree with me?
Yes.
So the hyperplane is the average of the in-between point on the distances or the vector W. Correct? Now, if I remove a few data points, won't the maximum change? Let's say I'm deleting 13 from this. Or the maximum changes?
No, I'm not saying consciously deleting the data points. I'm saying the data points are such that there might be two lines which have maximal margin between these data points. That's what I'm saying.
Okay. Okay. So your point is there can be more than one line. There can be more than one plane that ideally distinguishes both of them have the equal distance part.
Exactly.
Right?
Yes. Yes.
Now, in that sense and fashion, sir, so looking at this particular data, I will be able to say with some bit of confidence that only one hyperplane can exist here for this particular data.
Correct.
Even if a second one does exist, it is not, let's say I draw another hyperplane like this, but this hyperplane is unlikely to have the same distance or the highest distance factor between two classes. You agree with me?
Yeah, in this case, yes. In this case,
yes.
Yeah.
Correct? So in this case, this line is unlikely to have the distance. Now, if we look at this in a multi-dimension space, let's say I'm looking at it in a 3-dimension space, right? There can only be one planar separation that can exist that will distinguish the positive from the negative. Even if a second distance exists, I'll probably go with the logic here. Then in that case, it should overlap this hyperplane.
Yeah, for higher
order dimensions, it can only overlap this.
Correct. Right? Yes. They can
only only overlap this here. So the core objective going back is the distance metric between the multiple classes or the D, right, has to be the maximum, and the average of the D is what we call as the width of the hyperplane or the hyperplane that we design. So the reason I'm refraining from using too much of math is if I want to give you another answer to your question, the planar solution for how a hyperplane is designed in support vector machine is what we call as a quadratic convex optimization problem. So we have a Lagrange's derivative of distances that we compute, and from the Lagrange's derivative we look at how the two planars are supposed to be doing it in a polynomial equation. And from that equation, we extract a distance saying that this is supposed to be the exact distance between the two classes. This is the highest. So draw a plane that is the average of these two and use that as a separation boundary. So that is how the mathematics behind this works. Okay. Right. So it's an optimization equation that we solve to get the distance. So that is with some confidence we can say there can only be one distance that is the highest, and the average of that distance is what is used as a planar or hyperseparation between the two classes. Did I answer your question or did I confuse you too much?
No, yes, I understand. I understand that for higher dimensions, only one plane can exist. Yeah.
Right. Sure.
For the so this SVM is used when you have a higher number of dimensions, right? I mean, too many independent variables. So do we do we ever use, I mean, do we usually use any dimensionality reduction techniques like PCA or something else to basically, if you have so many high number of dimensions, I mean, do we still use those techniques and then probably come to this, or is there a limit that you have to have when you choose SVM? I mean, because there could be n number of dimensions, right? I mean, and then the examples are like 26 alphabets we have to choose or whatever, right? That the dimension is probably like 26, but it could be like hundreds or thousands. So
Okay, so to add an interesting spin, sir, just sorry to interrupt. A banking data set typically has around 5,000 variables. Use SVM there.
okay.
And just to add another thought to your point, SVM is very powerful. I'll tell you why. Because one of the techniques that you're about to learn, this technique is an image recognition or image tagging technique. Okay. Now, with that image tagging technique, we will be able to use an SVM with a radial kernel to distinguish multiple people. So a facial, in detection or in image processing, we have two particular problems. We have something called as face detection, and another problem is called as face recognition. All right. Now, with detection, it's pretty easy. Is there a face in that image? Yes, there is a face. Is there an object like a bat in that image? Yes, there is. If you have a recognition problem, you're talking about a face, whose face it belongs to, especially in a company, in an airport, in a lot of places. So you want to know whose face it is. So for a facial recognition problem, an SVM will add a lot of value. SVM will add a lot of power to this particular solution.
Okay.
Right, so this is the point we were talking. So reiterating also, so these points are called as the supporting vectors because they help me determine or compute this distance d, which helps me separate the margin of separation of my plane exists because of these vectors. So the vectors that lie in the edge and boundary that help me create this d and help me create the hyperplane, they're called as a supporting vector. This is generally how you look at it. I think I'm not going to talk about the math, but if you're interested, I'm always happy to have a complete lecture in math with all of you, right? But the idea, or I think what I want to discuss more is the rationale behind how the SVM works, and also talk a little bit about the math, right? So generally, if I want to give you a very quick math walkthrough, the entire concept of SVM lies on this preliminary fact of concept of vector calculus. Now, what we're trying to do is we have a known vector W that is perpendicular to the hyperplane that we're designing, and we have an unknown vector called U. Now, I want to know whether this unknown vector U, the dot product with my hyperplane, dot product with my known vector W, if it is greater than or equal to 0, then it is a positive class. If it is less than 0, then I call this as a negative class. This is a very simple explanation. So, or in other sense, we call this Wx plus b, right? If it is greater than or equal to plus 1, or Wx, the dot product of Wx plus b. If it is less than or equal to minus 1, we call this as a negative class or a positive class classifier, right? So this is a very simple math behind the product. I think this is what you will see on this particular. So you will see how the planar is determined, how the ideal separation comes into play, and you have this Wx plus by, which is the points of ABC and all these algorithms that come into play, right? So it's a pretty simple math, right? In terms of the basics. If I multiply this unknown vector U with my new known vector, perpendicular vector to the plane W, will it be beyond the perpendicular vector or will it be less than the perpendicular vector? So that's the key question, right? That's what we're trying to answer with the support vector machine, or in terms of the mathematics behind it, or the math behind it. Okay. You will have a lot of ways to pick the hyperplanes. You have the neural networks. You learn about them shortly. You will have the support vector machine classifier capability. So the perceptron technique that we're talking about is supporting vector techniques. We just want to talk about different data points that exist and how do you draw the boundaries on these data points, right? Right, so I'll give you one example, right? So let's say my data looks like this. Now, no matter how linear you do, your data is not likely to be segmented, right? So I can draw this hyperplane, I can draw any hyperplane, any side, anywhere, and we're going to end up with a lot of errors and losses. Correct? Now, this is where we have something called as the Murphy's theorem, where we can convert a low order dimension data into a higher order, right? I think this is the point we're talking about. Low order usually talks about x power 1. So higher order talks about x square, x cube, x power to the 4, right? And so on. So the basic idea, convert this into another dimension where I can now linearly separate the data, right? And draw my hyperplanes around it, right? So this is a key core advantage that support vector machines has to handle non-linearity of data, right? So won't you agree that this particular data is a completely non-linear situation, correct? Your typical linear approaches that we've seen so far might not be able to do anything in this particular case and context. You agree with me? So you'll find a lot of this non-linear data more in the real life as opposed to and as compared to more probable linear data points, right? I think that's the reason and the need to bring up or invent so much of these technologies and techniques that we keep talking about, right? So that's a very important attribute in terms of what is the support vector machine and then how do you go on about it. All right. So this is a Murphy's theorem or the dimensionality changes that we propose and generally get working towards. Okay. Typically, it's about x square and x cube that we kind of superimpose. I mean, we stopped to the third degree of polynomial. We can go up to 4, 5, 6, 7 multiple degrees, but right now third degree polynomial should be able to give us a nice clean separation and fit on the polynomial equation there, right? Right. So there are three parameters, three very important attributed parameters of support vector machines, and then they'll also add some key usage that is not discussed or the points not discussed in the videos as well, right? I think that's something that's very important. Now, the kernels, the whole idea, superimpose the data from a lower dimension to a higher order dimension, right? Now, before we talk about that, there are other things. I kept repeating this term called now I'll talk. Support vector machine has two classifier segmentations that we do, right? Two segments we talk. We talk about the hard margin classifier and the soft margin classifier, right? I'll talk about this. Now let me give you this particular data screen. I'll let the machine do the drawing and back at this. Now, sir, to this, if I typically draw my constraints, or if I have all the network constraints of maximum or maximize D applied and also my kernel tricks applied, how will the plane look for this? Can someone help me? Design this plane. You will have a plane that looks like this. Correct. This is typically because my network is a hard margin, which is it has least tolerance on errors. And it wants to keep the distance as high as possible, right? But this might end up, but I'll tell you the reality of the margin might look like this. This might be my actual planar margin that will give me the proper result. What I'm doing right now is called an overfit situation. Now, sir, so how do I handle this? Now, what happens is, to the equation that I have of my network fault tolerance, right? I have this capability of adding what I call as this slack variable. So this epsilon is called as a slack variable, and this cost controls this slack. How much of acceptable errors can I accommodate? How much of the errors should I accommodate, right? This is your cost factor, right? One of my parameters cost of penalizing the error and cost of accepting the error. This is the parameter called as my cost. Out of the three parameters I have called my kernel, cost, and gamma, this cost determines the acceptance or the tolerance of errors in my network and model. Right, so let's talk about it. So, the support vector machine is useful in a multi-class problem also, right? In a multi-class classifier, the key important attribute is, or there's an interesting aspect is the decision function shape that will determine. So OVR is called as one versus rest, and OVO is called as one versus one. What do you mean by that? Very simple. In a multi-class problem, if I want to draw the hyperplane, should I consider one versus rest first, and then draw the hyperplane or give its margin first? Or should I consider one versus one, draw the hyperplane, one versus one again, draw the hyperplane, and then this do the same probably here and get this planar? So the key question is, should one versus one be looked upon or one versus rest? The default option is one versus rest, which means that look at all classes before you start drawing a planar individually. But the idea is you have this parameter as a configuration option where this will now draw this and draw these planars. So the key point to remember, again, the distance has to be maximized. The points on the edges are called my supporting vectors. And I am now going to use the distance function shape to say whether should it be one versus one or one versus rest. So this is also a parameter that we can control with the decision function shape in the support vector machine. Similarly, so degree of polynomial default is 3. I can control this in the parameter where I'm passing to the model also, right? So this is in short what I had as theoretical components for support vector machine. So I'm more than happy to take any questions if we have any right now, right? So it is pretty strong or pretty robust algorithm, especially nonlinear. So you have the bioinformatics, the gene classification, protein classification is strong, which is in a very high dimension scale. It does wonderfully well.
Yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes, you can use this for a spam ham classifier, where or you can do it for a sentiment classifier as well. But text, I think best said is there's a lot of pre-processing involved before I come to the phase of fitting a model to the equational scale. There, sir.
Yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes, you can use this for a spam ham classifier, where or you can do it for a sentiment classifier as well. But text, I think best said is there's a lot of pre-processing involved before I come to the phase of fitting a model to the equational scale. There, sir.
Yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes, you can use this for a spam ham classifier, where or you can do it for a sentiment classifier as well. But text, I think best said is there's a lot of pre-processing involved before I come to the phase of fitting a model to the equational scale. There, sir. Right? Not to discourage the question, but the key idea is with text you have to do something called as a feature engineering part, where
yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay. Yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes, you can use this for a spam ham classifier, where or you can do it for a sentiment classifier as well. But text, I think best said is there's a lot of pre-processing involved before I come to the phase of fitting a model to the equational scale. There, sir. Right? Not to discourage the question, but the key idea is with text you have to do something called as a feature engineering part, where should I go for a bag of words approach, bag of words plus TF-IDF, or bag of words plus count vector, and convert my text data from its raw form into a machine readable format, and from there build a model of classifier of some kind. That's the key question that we have. But yes, this is robust towards a lot of dimensions. Text analysis or text classification usually has a lot of dimensions.
So
Right.
when you talk about this image classification, like does it also talk? You do also talk about this face recognition as well, like.
Recognition per se, it cannot be used natively. So there are.
Yeah, so yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes.
Yeah, so yeah, that is one question. So the text categorization. So is this also used for the spam ham and all? Yeah, so yeah, that is one question. So the text categorization. So is this also used for the spam ham and all?
Yes, sir.
Okay.
So for text classification, yes, you can use this for a spam ham classifier, where or you can do it for a sentiment classifier as well. But text, I think, best said is there's a lot of pre-processing involved before I come to the phase of fitting a model to the equational scale. Right? Not to discourage the question, but what we're going to look at right now is a cancer study or the breast cancer reduction data set from Kaggle or archive UCIs that we have. The various data sources, we're going to use one. So we're going to use historical information, and we're going to study about the patient records and patient information, right? So I'm giving you the link to the dataset as well. So please feel free to explore other datasets in this particular archive. Okay. First, let's import the libraries. We have the matplot, we have the seaborn layer, all these things. Let's read the dataset. And let's look at the. So this is the dataset we have. Right. So I have the ID that talks about the patient ID, the term thickness of the breast cancer data set, the cell size, the cell shape, the marginal adhesion, the single epithelial cell size, the Barney, all these things, right? So these are data fields I have. Okay. Now we talk about close to 700 records. We have information from 700 patient records. Okay. And let's look at the dataset information. I'll say dataset.head. The different information, all these are hard-coded encrypted values. Right? So if I talk about describe, you'll understand this even better. So the average is somewhere around 3.2. The standard deviation is 2.97. The max is 10. And all these are encoded values is from what we'll be able to gather from this information. Right? So let's use this now. Let's convert this and let's see. Remember we talked about the other day. We said we had question marks, so we wanted to check. So right now we're filling the question marks with median values. Right? Median meaning the most occurred value. So I'm finding out this, replacing the question marks with NAN. And when I replace this, I have this apply function. Now apply function will iterate over every row, right? And that is what you'll find as the X value. So lambda is basically a function where I'm saying, take that row and fill that NA with the median value of that particular column, of median value of that particular attribute, and do it on the row. Do it on the row level. Okay. So this is the function. So the apply function is a lambda function. So I can use apply and lambda. So lambda is a one-line function where I'm saying export these values and use that to build the information. Okay. Okay. Moving on. Let's quickly find out the null values if at all they exist, and they don't. Okay. Now let's start building the model. Let's create the train test split first, and let's create the feature state. So can someone explain why we need a random state and what's the objective behind it?
To always go get the same set of training and test.
Absolutely, right. So just to ensure that we get the same records of training and testing every time, we are right now using this the random states, so that if we do this, it will remind the memory, it will create an anchor point in the memory and give us the same sample every time. Okay. Right. Now that we have the training and testing records done, let's now start building the model. So sklearn is a separate package all in itself, and I can now import. If someone say import SVR or SVC, I'm doing SVC. I'm setting a very low cost. I'm having a linear kernel, having a gamma of 1. So this shouldn't matter by default. If I fit it, you will find these parameters. So the attributes that we were discussing, the decision function shape, it is 1 versus rest. If I'm applying a polynomial, by default, the polynomial kernel is 3. And I think this question did come about. Just wanted to reinforce this point here, right? Is this point clear, sir? So the default is a 3rd degree polynomial, and I'm getting the gamma as 1. If I don't set the gamma, I'll show you that also. By default, it's called auto enabled, right? Auto disabled or auto enabled. I'll show you that. So the kernel is a parameter I pass. Okay. Now I'm going to make a prediction on the testing sample. All right. So this is the accuracy we're getting with the linear kernel with the parameters we specified, right? So the trade-off seems to be a fairly reasonable trade-off, where I'm looking at the exchange score and the excess score, right? Between the training sample and the testing sample, I'm not having too much of variations, which means that the parameters we pass are sufficiently good in fitting this particular model, right? So the confusion matrix, I'm having a decent sanity, right? I'm having very few false positives with a very few false negatives, right? So let's build the RBF kernel. I'm not setting any other parameter. By default, the cost is 1. The gamma is auto deprecated, which means that I'm not going to pass it. It's automatically set to the lowest value possible, right? And my tolerance is 0.001. Okay. Now, sir, if I fit to this particular data, I'm having a brilliant accuracy with my training sample, but my testing suffers. Now, let's look at a polynomial kernel. How it works for this data. And to be told, it's a completely overfit model. Don't you all agree?
Shyam, just a question on the previous step. So in real time, the test data. So right now we are comparing the trained data accuracy versus the test data, right? But in real time, right. Is it a good practice to do that? I mean,
okay. So right, let me put this point forth, sir. So the objective that we're trying to achieve here, right, in terms of looking at the train versus the test, is to effectively understand the model's capability and the model's sanity. And the sanity is a generalization error or generalization acceptance that I'm essentially trying to equate here. So which means that if I build a model on my training and I have a real world unknown sample, in this instance, the testing sample I split out from the data set I had is an unknown or an unseen data according to my model. You agree?
Right.
Which means that the model has never seen the data to essentially learn about those parameters. So from the learning it's done from my training sample, I'm trying to see how it is performing on an unknown data sample with the parameters I've learned from my training. Now, having with that condition in place, is how's the model doing? That is the evaluation I'm doing here. So unless I do this evaluation, I won't be able to, honestly get into a proper deployment or use this model to predict the real world cancer cases in any situation and sense.
Right, but then in your experience in real world practice, so let's say right now we have that visibility into the test data, so we are making a comparison to understand the effectiveness. But let's say the train and the test worked fine, but then now we are going into the deployment phase. But then those are greater unknowns. So will the model tweak itself or?
Yeah, so the model will not tweak itself. So from my experience, right? So right now, while we're deploying for a real world problem, right? So we're deploying for a forecasting problem we have. And what happens is we right now have the base data that we have as part of the historical dump. We take a training and we take a testing sample. And only if the testing sample of all the approaches I've used are if they have, that I've enabled, if they're doing a fairly good job, will I even go for an approach to fit this stuff? Otherwise, I won't be able to deploy my model at all.
I think that testing is also an unknown data to a model. So I think that is what is
Yes.
questioning. So
Yes. So
yeah, so the model only knows
that
the training
testing is
data.
unknown.
Right.
Like the model only has seen the training data. It has never seen the testing data. The real world is even more, right? It means
Right.
that I don't even know. With the testing data, at least I have a column where I can compare the accuracies and compare the efficiencies of the model, right?
Hmm.
But with the real world, even I don't know the target column unless until the results actually come in, unless until the values start filling in. Even I won't know, right? But I know the acceptable rate or the error rate I have, or the tolerance rate I have towards different classes and different effective solutions I'm building. So to make sure that I know what I'm doing is why we have this option of let's say a training sample versus testing sample accuracy and the model results that we're doing.
Ansham, when we choose this, this accuracy comparisons, right? So, do we always choose for like a training and testing accuracy which are close by?
Right.
Let's say there is a training is 90 and testing is 85, and we have
Right.
other polynomial kernel where we have a training as 81 and testing as 80.
Right.
You try to go with the second latter one, right? Because
So the general option is test minus train divided by train accuracy should not exceed or fall below 15%, plus or minus 15%.
Okay.
So the situation exceeds, we call the present scenario as an overfit or an underfit based on the equation.
Okay.
Right? So this is how we compute. So with respect to the test training accuracy, how does the testing accuracy perform? So we call the situation as an overfit or an underfit based on this particular situation.
Okay.
All right. And there's also another parameter that we use to choose that we have to determine the optimal hyperparameter. They are something called as the bias variance trade-off. So you learn about the bias variance trade-off shortly. But this is also something we use to determine the optimal parameters for a model along with the grid search. And you'll also know about using this optimal parameters, we do this overfit or underfit comparison. If it doesn't exceed or if it falls below, then we say the model is an overfit or an underfit.
When you say optimal parameters, you mean the accuracy and
right. So
metrics.
basically, we have multiple combinations, right? So I can go from cost of 0.001 all the way up to cost of 100. Right?
Okay.
Which one should I choose to essentially get this best possible model for my current scenario? Right. So this is always this question of which is the best option, right?
Right. Okay.
This is something called as a grid search, right? So with the grid search, you'll select the dictionary of parameters you want to pass, and then you will use those parameters to ideally, create and combine, or you might iterate over multiple options before coming up to the final and the best possible data. So this kind of concludes what we had in store for support vector machines, the theory and the practical components attached to it. Right? So I'd love to take any number of questions right about it. Right? If there are no other questions, we can wind up the session for the day.
This brings us to the end of this tutorial on support vector machines. Now, before I sign off, I'd like to inform that we have launched a completely free platform called as Great Learning Academy, where we have access to free courses such as AI, cloud, and digital marketing. So thank you very much for attending and have a great learning ahead.